Welcome back to part 3, polymorphism. What is polymorphism, I hear you ask? Like many words in the English language, polymorphism derives from Greek. Poly means many and morphs means forms. So in this case, polymorphism literally means many forms. When we mean forms, we really mean unit cells. I hope you remember from considering earlier sugar, that the molecules of sucrose can pack into more than one unit cell. So I had one unit cell in blue and a different unit cell in green. The way that the molecules pack in those unit cells might be different. So on the screen in front of you are two general diagrams showing you how one particular API, in this case it's a dark red cube, might pack into two different arrangements, form 1 and form 2. I hope you can see that the way that the molecules are arranged in form 1 and form 2 are different. Form 1 seems to have more space between the molecules than form 2. If you're saying to me, where is the concept of unit cells in this particular instance, Simon, because I'm not following, unit cell is the smallest repeating pattern that we need to define in order to describe the particular form. So in form 1, we could draw a little rectangular cube around the first 3 molecules. So 1, 2, 3, we could draw a cube around that. That would be our unit cell, and that unit cell is then repeating to build up our pattern. And the same is true for form 2. We could also draw a cube around the first 3 molecules. That's 1, 2, 3. That would be our repeating pattern. Those unit cells are different, but they pack together to create the different physical forms, okay? 2 different polymorphs. So it's important, polymorphism means a material with different unit cells, not different habits. If there's an exam question about polymorphism and it says define polymorphism, and you say polymorphism means a material can exist in more than one habit, that's wrong. If you say polymorphism means a material can have more than one unit cell, that's the right answer, okay? Why is this important? It's important because when molecules pack together, it impacts how the macroscopic crystal is going to behave. So if I give you some examples, form 1 is shown on the left on the screen, form 2 is shown on the right. You don't know anything about the chemistry of this molecule because right now it's just a burgundy square. You've got no idea what the chemistry is. But if I said to you, which one of those two, looking at them, would have the lower density? I hope you would say form 1 looks as though it's got a lower density than form 2 because there are more spaces between the molecules, and I would agree with that. So form 1 looks as though it's got a lower density. Form 2 therefore has a higher density. Lattice energy, that's a tricky one. So lattice energy is how much energy we have to put in to the crystal to be able to break it apart, okay? So in other words, it's about how much energy is kind of how strong the bonds are that are holding the molecules together in the crystal structure. Again, I hope you might see that on the left, the molecules don't look very closely packed together. So if there are interactions between them, they're probably quite weak. But on the right, the molecules are quite highly packed, and so the chances are they are interacting quite strongly. So if we were going to try and put energy in to break the crystal structures apart, we probably need to put more energy into form 2 than into form 1, and therefore it has a higher crystal lattice energy. It's the amount of energy we have to put in to break it apart than form 1, so that's important. Melting point is a temperature, but it's related to how much energy we have to put in to break the molecules apart. Therefore, if form 1 has the lower lattice energy, it means less energy to put in to break the molecules apart. It's going to have a lower melting point. It's always the case that a lower lattice energy means a lower melting point, and a higher lattice energy means a higher melting point. So right there we can differentiate between those two forms. The next one down you might or might not be familiar with, but you can calculate this concept called ideal solubility. We are not going to look at ideal solubility in this lecture. So I'll just tell you that a lower melting point means a higher ideal solubility, and a higher melting point means a lower ideal solubility. Maybe that's a concept you'll come back to at some point in degree, but for now just accept it. And then a faster dissolution rate for form 1, a slower dissolution rate for form 2. Again, it's because we have to separate the molecules from the crystal structure to get them into solution. So we don't know anything about the chemistry of our burgundy squares, but what we do know, just by looking at how closely or not they are packed together, we can have a bit of a guess as to which one's going to have different physico-chemical properties. And in the real world, if we make two different polymorphs of the same molecule, we will also see differences in properties like this. And it's kind of important that we choose the polymorphic form to turn to a medicine which has the right properties for what we want it to do in the body. Now, I am a thermal analyst by training, which means I use a technique called calorimetry. In fact, if you come upstairs to my labs, we've got loads of calorimeters, it's tremendous. And it also means that we do a lot of thermodynamics. Thermodynamics is one of those words that generally makes students fall asleep. And indeed, you may have fallen asleep now watching this video, but I'm not going to know. It's much more obvious in the John Hanbury Lecture Theatre when people fall asleep, because I can see it right in front of me. However, it is important to look briefly, at least, at the thermodynamics of what's going on here, because it's our way of ranking the relative importance of polymorphs by looking at their thermodynamic properties. One of the key things to remember is the form with the lowest energy is the most stable. Now, when I taught this last year, this was one of the other concepts that kind of confused a lot of people. So one thing to remember is that in nature, spontaneously, most things progress to the lowest energy level. Okay, so lowest energy level. So if we've got molecules and they want to condense into a crystalline form, they want to go to the lowest energy form. The lowest energy form will be the most stable form. Now, I find with crystalline materials it's sometimes more helpful to think about destroying the crystal structure than forming it. So bear with me. Imagine that you've got a crystal structure in which the molecules are really, really tightly packed, like this. Each one of these, each one of my fingers represents a sucrose molecule. Imagine that they're in a crystal structure which is really, really tightly packed, like this. The molecules are really close. I hope you can imagine from the previous slide we just looked at, this is probably going to be a stable polymorph because the molecules are really well packed together like this, and that they're interacting quite strongly, which means that in order to break these apart, we have to put quite a lot of energy in to break the bonds that are holding these molecules together. Okay, this is where it becomes slightly confusing for people. So the strength of the interaction holding these molecules together is the highest, but this is the lowest energy form. That's where people get confused. So the bonds between these molecules are the strongest, but this is the lowest energy form. Why? This is where I think it helps to think about breaking this apart. This is my crystal structure. Imagine I want to melt it, for instance. If I'm going to melt it, I need to add energy. I need to add enough energy to break the bonds that are holding each individual sucrose molecule to my crystal lattice. Because these molecules are really, really tightly together, they're interacting the strongest, which means that the amount of energy that I need to put in to break it apart is going to be the highest. Okay, so if I'm going to go from this crystal structure to something which is melted, I have to put the most energy in to make it melt. Therefore, imagine that I started with a molten solution, molten liquid. Sorry, a liquid, not a solution, a liquid, and I was to reduce the temperature, and the material crystallized. If I go from a liquid to this very well-packed crystal structure, because I've had to put the most energy in to make it liquid, when it condenses back again to the crystal, it will effectively lose or liberate the most energy, won't it? If I have to put lots of energy in to break this apart, when I form it, I get lots of energy back again. The process is reversible. So this crystal form, which takes the most energy to break apart, is the one that lost or liberated the most energy when it formed. That's where people get confused. This is the lowest energy crystal structure, but the lowest energy crystal structure means the ones where the bonds holding the molecules in place are actually the strongest. People get confused with that. So just think, how much energy do I need to put in to break this apart? A lot. And therefore, when it forms, that energy is liberated. It liberates a lot, and it's the lowest energy form. So the most stable form is the lowest energy form. Any other crystal form that might happen, let's say something like this, which is less well packed, if I were to melt this, I have to put energy in to break these bonds. I have to put less energy in to break these bonds because they're not so strong, and therefore when this forms from solution, it liberates less energy. Okay, so the most stable form is the lowest energy form, and every other form has a higher energy level and is termed metastable. It means slightly less stable. This is kind of important. So if we have a drug molecule, I keep talking about sucrose, but let's think about ibuprofen, for instance. Imagine ibuprofen can crystallize like this, or it can crystallize like this. These are different polymorphs. This one is less stable than this one. What does this mean? If I swallow ibuprofen, for instance, when I swallow it, the ibuprofen crystal has got to dissolve, so the molecules go into solution, so it can be absorbed. There's less energy that needs to be put in to break this crystal structure than this one. So therefore this one, which is the metastable form, it should dissolve faster. Because it dissolves faster, it should get into the blood faster, and so we should see a faster bioavailability. This one, which is the stable form, takes longer to dissolve because it needs more energy, and therefore we see a lower bioavailability. Okay? So again, when we're thinking about formulating a medicine, we have to think about the crystal forms that we can get the drug in. A metastable form is probably going to give us a better therapeutic response than the stable form. Think back to the start of this lecture, and I said, why then do most pharmaceuticals, why are they not amorphous forms on the market if those are the fastest dissolving? And the answer was they are the least stable, and so on storage they're going to crystallize probably. The same is true here. Why do most drugs on the market exist in the stable form, not a metastable form? The answer is because stability. The pharmaceutical industry is concerned about stability. And if your product performance is dependent upon the crystalline form being a metastable form, it's a little bit risky because on storage, your metastable form might convert to your stable form. We're going to come back and have a look at that in just a little bit of time. On the screen in front of you is a diagram showing you the stages through which a tablet in this case has got to pass in order to get into the bloodstream. So you start with your tablet on the left hand side, which the patient swallows. You may, depends on the properties of your material, granulate that material and put it into a capsule. It doesn't really matter. Or maybe when you swallow that tablet it starts to disintegrate and form large granules, which then as they start to break down will become small particles. Once those small particles dissolve, the molecules are in solution in the GI tract somewhere, maybe in the stomach if it's an immediate release tablet, maybe in the small intestine if it's a more extended release tablet. And then once the drug is in solution, it can be absorbed across the gut wall. What happens in the process of dissolution, and we have talked about this briefly, but we're going to look at the thermodynamics at this point. We have to break solid-solid bonds in order to get the molecule to dissolve in solution. So each of my fingers is a molecule in a crystalline lattice. For it to dissolve, we have to break a molecule from the crystal lattice first, and we have to put energy in to do that because we've got to break a bond. There's an existing bond. Energy has to be put in to break this bond. Okay? From a thermodynamic perspective, putting energy in to something is called endothermic. We're adding energy, it's endothermic, and by convention that's given a positive sign. So when we have to start with a solid material and we want to break it apart, the first thing we have to do is put energy in. We are effectively melting the material actually by putting energy in, and so that step is endothermic. Then once that molecule comes off the crystal lattice, it interacts with the solvent. It's usually water, especially in the human body unless you've been drinking a lot, so it's generally water, and so you're going to form bonds between the molecule that's just come off and the water. Obviously if there's a degree of solubility in water, then that's going to be a favourable interaction. Favourable means energy is given out, and that is exothermic, and by design that's given a negative enthalpy. So on the screen, top line shows you breaking of solid-solid bonds, which is endothermic. Bottom line shows you the forming of solvent-solid bonds, which are exothermic. So we have this balance between endothermic, to break the crystal apart, and exothermic, forming interactions with water. Usually, it can be any other solvent. At the top of the slide is the famous equation, delta G equals delta H minus T delta S. I know that you love this equation. Delta G is the free energy, and for a process to occur spontaneously, it needs to be negative. If you look at the equation, how is delta G going to be negative? It's going to be negative if delta H is negative, because T delta S is always positive, and therefore minus T delta S is always negative. So if delta H is negative, minus T delta S, it has to be negative. The free energy has to be negative. So if a process is endothermic, the chances are it's going to occur spontaneously because delta G is going to be negative. The issue arises if delta H is positive. The only way delta G can be negative if delta H is positive is if the minus T delta S term is bigger. Okay, so if we have a small endothermic delta H, so a small positive endothermic delta H, but the T delta S term is much, much bigger, then the process can occur spontaneously. So it's not always the case that an endothermic event won't occur spontaneously if the T delta S term is bigger, but in the main it's kind of unhelpful if the delta H term is positive. Why am I talking about this? If you think about the slide before, we had breaking of solid-solid bonds, which was endothermic, followed by solvation of molecules, which was exothermic. And so we have a balance, endotherm, exotherm. It is kind of important that if it's going to dissolve spontaneously for a particular material, that balance, it really wants to be negative. Because if you've got an overall exothermic process, the T delta S term is bound to be negative. The delta G is going to be negative. And it is possible that in some instances we have an overall endothermic enthalpy of solution, but it just means it will dissolve much more slowly. This is a classic example. It's in Alton's Pharmaceutics, actually, if you have a look. It's the dissolution of chloramphenicol palmitate, and it's got two different forms, form A and form B. Form A is the stable form, and form B is the metastable form. So on the graph, the pink circles show you the bioavailability profile if you administer form B, pure form B. So form B is the metastable form. Remember, metastable means faster dissolving, so you can see you get a much more rapid increase in blood serum level, followed by excretion. The blue or grey solid circle shows you what happens if you administer 100% form A. So 100% form A is the stable form. You can see you get really poor serum concentrations because the form just doesn't dissolve in the first place. So it never gets into solution. So it can't cross the gut wall, get into the bloodstream. Can you imagine what will happen if you go to the regulator and you say, right, I've got this formulation of chloramphenicol palmitate. This is its bioavailability profile, and I need it in form B in order to get decent blood exposure. So the regulator says that's fine. How stable is form B? Is form B stable for a week, a month, a year? You have to answer that question, because if form B, which is what you put in your product, converts to form A after a month on storage, what would that mean? It would mean that a patient taking that tablet after a month would get the exposure shown in blue, not the exposure shown in pink, and that would be really bad. So in this instance, changing of the physical form of chloramphenicol palmitate in a product would lead to the loss of the performance of that product, and it would be really bad. So you have to demonstrate to the regulatory body that you're going to make a product which is metastable, so unstable, but that it's going to be stable over the shelf life of your product. Because if it isn't, it's not going to perform as you intend. And actually, if you look at the monograph for chloramphenicol palmitate, you'll see that there is a legal limit on how much form A can be in the formulation, and it's 50%. And the reason is because if you give a mixture of 50-50 forms A and B, you still get decent blood exposure. The reason is because not all of the drug is actually crossing into the bloodstream in the first place. So you still get good exposure if you've got 50% form A, 50% form B. But you have to justify this to the regulatory body. And this is an example where if you change the physical form of your drug on storage, your product isn't working anymore. Before we stop for yet another tea break, we're going to look at hydrates. So you may have heard of hydrates. Hydrates are a special type of polymorph. And it's a special type of polymorph because not only is there the drug in the unit cell, there's also water in the unit cell. It doesn't have to be the case that there's one water molecule for one drug molecule. If there is, then it's called a monohydrate. One drug molecule, one water molecule. It may be, for instance, that there are 2 water molecules for every drug molecule, in which case the material is a dihydrate, 3 water molecules is a trihydrate, and so on. Critically, there will always be a stoichiometric ratio of drug to water. So it will always be a ratio, 1:1, 2:1, 3:1, whatever. Always a stoichiometric ratio. That is not important right now, but when you do analyses of things to determine whether they're hydrates or just wet later on, then it becomes very important. So stoichiometric is always an indicator that the material is a true hydrate. So in this case, you've got in the unit cell drug molecules and water molecules in your unit cell. Why is this important? Most people think that if you add water into your unit cell, and so you make a hydrate, that would be better. It would be better because you're effectively pre-dissolving your material, and so it should dissolve in water to a high level. Now, actually, when you make the measurements for real, the opposite is true. Usually a hydrate has a lower solubility in water than a corresponding anhydrous material, which can be a bit odd. Most people think there's lots of water knocking about, and that's a good thing. You've pre-dissolved it and it should be good to go. Why do you think that might not be the case? Just take a moment to think about that. Yeah, I'm thinking about it too. Have you come up with a plan? The answer is that water is a really strong hydrogen bonder. So if you've got drug in your unit cell, and you've got another drug molecule in the unit cell, and you have water molecule between them, the water can form hydrogen bonds really strongly with your drug molecules. Effectively, the water starts to bind your drug molecules together even more tightly than if it was just drug molecules because of the capacity for hydrogen bonding. Okay, if you think about what happens when you dissolve a crystalline material, you've got to put energy in to break the bonds that are holding the molecules together. And if there's a lot of hydrogen bonding because the water is there, you've actually got to put more energy in to break this apart than you would do if the water wasn't there. It's kind of counterintuitive. And so quite often hydrate materials have worse solubilities than the anhydrous form, which is kind of surprising. One of the reasons for understanding this is because some crystalline forms can absorb water on storage and form a hydrate. And so you think you're formulating an anhydrous form, but actually by the time the patient takes it, it's a hydrate form. So on the screen is the same equation as before, delta G equals delta H minus T delta S. We know what needs to happen here, balance of terms. Delta H really wants to be negative, minus T delta S is going to be negative. It's very important that in this particular instance, think about what's got to happen. You've got to put energy in to break the bonds that are holding the molecules together. You've got to put more energy in because of this hydrogen bonding. So that's a barrier right from the start. But then the second step, which is when you get some of that energy back again, when the molecule interacts with water, that's already happened because the hydrate, the water of hydration is already in your unit cell. It's already interacting with your drug molecules. So some of that interaction where you get the energy back again has already occurred. So you've got this double whammy, more energy in to break the bonds apart, and then some of those bonds have already formed. And so the chances are your delta H term is going to be way less negative or more likely slightly positive when you've got a hydrate. And so that means that the free energy is almost certainly going to be positive or only very slightly negative. So as an example, I think it's the last slide before we stop for another break. The screen, you can see serum levels of ampicillin as both an anhydrate and a trihydrate. So the anhydrate, unsurprisingly, is the curve with the higher bioavailability and blood serum levels, and the trihydrate blood exposure is less because it's harder to get it into solution. Right, with that we are good to stop again. When we come back, we're going to talk about amorphous materials.